So how to design a two-way slab? Which tables you can use and how to, what is actually is a two-way slab means what? Which is more economical, whether two-way or one-way slab? Everything you can see here. So as you have seen here, in case of slabs, you should be able to design one-way slab, two-way slab, and continuous slab. So I will wherever critical the steps are there, I'll be going slow there. Easy steps I'll go fast now because deflection and all is already taught. But you have to read the notes, complete one-way slab design, how it is designed, means what are the total all steps. All steps you should see for one-way slab, which I will be giving you the notes today. So two-way slab is, you observe this. Two-way slabs are supported on all four sides and Ly by Lx ratio will be less than or equal to 2. Less than or equal to 2. It means it is little bit squarish in plan. Squarish, almost very close to square because it is usually 1 or 1.5 like that. It doesn't look like a rectangle when you see it. It can be a rectangle of small variation. That is why Ly by Lx should be less than or equal to 2. Then only we can design it as a two-way slab. See, all of you mute it. So in two-way slabs, bending takes place in both the directions. I'll show you that one. In case of beams, bending takes place in only one direction. In case of one-way slab also, bending takes place in only one direction. But in case of two-way slabs, bending takes place in both the directions. So you have to find out bending moment along this direction, along this direction here. In both the directions, you have to find the bending moment and provide the steel required. So main steel is provided in both the directions. So these are the basic differences, basic information regarding two-way slab. Main steel is provided in both directions. Bending takes place in both directions. Ly by Lx is less than 2, supported on all four sides. Sometimes it will be supported on just 3 sides also. Or sometimes it will be supported only on 2 sides also. Those cases are there. But initially we have to go through this one, that is all four. The slab is supported on all 4 sides. All 4 sides beams are there, or all 4 sides wall is there, like that. Wall or beams and column system is there. So this is what we call it as two-way slab. What are the differences between one-way and two-way slabs? You can see one-way slab here. Ly by Lx is more than 2. You can see how it looks. It looks a big rectangle. A big rectangle. Main steel runs along shorter span. Ly is short span. Lx is short span. Ly is longer span. You can see here. Whatever I have drawn this etching is done. Those are the supports. So those are the supports. Main steel has to rest on the supports only. That is why main steel is along the shorter span, that is Lx. In the other direction, it will be distribution steel. We call it as distribution steel. So Ly by Lx is essentially more than 2. If this is 3 meter, it has to be more than 6 meters. The meaning here is, if Lx is 3, Ly has to be more than, means it has to be 6.5 like that. So Ly by Lx becomes more than 2. Similarly, here if you see two-way slab, Ly by Lx should be less than or equal to 2. It is either less or equal to 2. If it is more than 2, it is one-way slab. Supported on 2 sides, that is one-way slab, supported on all four sides. So main steel is provided along short span. In case of one-way slab, main steel is provided in on both short and long spans. It means you can see how the diagram is drawn here. Inside whatever I have shown, what it indicates, main steel is running along x direction as well as along y direction. Depending upon the moment, bending moment along x and along y, we have to calculate separately. Less economical. That is, one-way slab is less economical. The reason is the thickness and steel are more. So one-way slab it requires more thickness as well as more steel is required, because here not only you have to run the steel in this direction also. Don't be under the impression that steel requirement will be less in one-way slab. It is not like that. When you check the designs here, you will find that steel requirement is more in one-way slab as well as the slab thickness required is more. So this is the differences. Usually they're asking what are the differences between one-way and two-way slabs. Now coming to this type of two-way slabs. Restrained two-way slabs, table 26 of page 91, IS 456. Unrestrained two-way slabs, table 27 of page 91. Unrestrained is easy, restrained is lengthy problem. So I'm going to solve restrained first, whichever is lengthy, that will be solved first, so that we can easily follow unrestrained two-way slabs. Usually they are asking restrained two-way slabs in the examination because unrestrained is a little bit easier than restrained. What is unrestrained and restrained you will understand later on. So this is what is about your this one, that is two-way slabs. Let us go to the next page. Steps involved in the design. You can see steps in the design of restrained two-way slab. Restrained. Corners are held down. Corners are prevented from lifting. That you will learn later on. Only thing is that either it is called as restrained slab, restrained, or one more name for restrained two-way slab is corners are held down. All the corners are prevented from lifting here. So here we have to go for table 26, page 91 of IS 456. I have already, I'm having in this particular discussion that page is already there. Step number 1, check for the type of slab and determine the factored load WU. Type of slab means simply find out Ly by Lx ratio. If it is less than 2, you can say I am going to design two-way slab. In the problem, it will be clearly given whether the slab is restrained or unrestrained, so that you have to use either 26 or 27 table. If it is unrestrained, you have to use table 27. If it is unrestrained, that is why they have to give in the question paper whether it is a restrained or unrestrained two-way slab. Second step, determine the effective span LE, factored bending moment, MU limit. One more I missed here. Factored shear also you have to calculate. Factored SF, WL by 2. And MU limit to see if the section is under reinforced or not. What it means here is factored bending moment and MU limit values are compared. MU limit has to be more than factored bending moment for the assumed thickness. Step 3, reinforcement. Reinforcement along the short span, along the long span in the edge strip. Just observe this figure here. Let us say this is your okay, I'll draw this figure here. Let us say this is your two-way slab. Okay. Now, what is the meaning of this third step? Third step, what it says? Steel has to be provided reinforcement after finding bending moment reinforcement along the short span, along the long span in the edge strip. So let us see this one along the short span. This is the, let us say this is the short span here. Lx is less than Ly, but ratio is less than 2. When we provide the reinforcement in this direction, we call it as reinforcement along the short span, along Lx. Like this, you have to provide the, how to provide the reinforcement is a separate talk only. It cannot be covered in this. Then reinforcement along the longer span, Ly. Diameter and spacing we have to calculate it, finding the bending moment using table 26. Reinforcement in the edge strip. So here what happens here is, what exactly it means. Actually whatever I am showing here right now, how it should be provided actually. Let us say this is, you can see this one. We have to get this edge strips. Imaginary lines are there like this. This is one edge strip. This is another edge strip. It is like this. Now carefully observe this one. Two-way slab reinforcement, how it is done. How it is done, you observe here. So in the middle strip, whatever this is there, this is, we call it as middle strip. These are all imaginary lines divided with suitable dimensions. I'll give you that one. So here you provide reinforcement in the shorter span like this. Whatever I have shown red color there, this is provided here. It means theoretically only in this middle strip reinforcement is required theoretically, because bending is maximum in this. How it bends, you imagine a cup and saucer. Cup with saucer, you remove the cup and look at the saucer. In the saucer way it is going to bend. Okay, the bending takes place in both the directions. Now this again reinforcement along the longer span is this. Theoretically I'm telling. Now, whatever I'm telling here, whatever I'm telling in case of third step, along short span, along long span in the edge strip means this diagram. Will you this only look at this? Red color along short span, green color bars are along longer span. Theoretically, only in this area of the slab. Actual slab is this. Total slab is this. In that one, middle strip is this much. I'll give you dimensions of all this. Edge strip means all this edge, continuous edge it is, peripheral. Whatever is this edge strip is there, no, we don't need more steel here. We need less steel. That is why it is more economical than one-way slab. It means in the edge strip, all along there are 4 strips are there. In this area, we are going to provide only minimum steel. Minimum steel is provided. That calculation I will show you there. So this is how the reinforcement is done theoretically. This is a theoretical diagram. Theoretically, it is divided into 3 parts along x-axis. One is edge strip, middle strip, one more edge strip. Along y-axis, it is divided into 3 parts: edge strip, middle strip, then edge strip again. That I will make it clear in that while solving the example. Reinforcement has to be calculated like this. Okay. Next is torsional reinforcement at the corners. So one simple formula is there for that. I'll show you in the while solving the example how to get it. It's a very simple formula is there. Just you have to provide at the 4 corners. Check for shear as it is as usual. It is table 19 and all same procedure is followed. Find the shear capacity of the slab and compare that value with WU by L. I mean WL by 2. In case of slabs, shear capacity is maximum because of the value B. B drastically increases the shear capacity. The reason is TOC into BD. Shear capacity formula is TOC into BD. B is 1000 here. You can see B is 1000, whereas in case of beams it is hardly 230 mm. Since B is very high, No need to provide any stirrups in case of slabs. Shear check is actually not required. Usually in the examination, you should first do check for deflection, more important than shear, because it is always, slabs are always safe in shear. You can go to any site, there are no stirrups in the slabs. The reason is simple. Shear capacity is tau c into BD. B for beams is 230, B for slabs is 1000. So shear capacity is very high. Then sketch the details of reinforcement. Check for deflection, again page 37 of IS 456. So you need to practice these two now. You need to practice step 5 and 6 for beams. For slabs, even if you leave this check for shear in the examination, you can say that slabs are always safe. Usually they are safe in shear. But the best is tau CBD how to calculate. Simply calculate tau CBD, compare with VU. That's all. Shear stirrups are not required. You have to write. So the examiner is more bothered about here. Examiner is more bothered about check for deflection, because he also knows that no stirrups are there in slabs. So this is these are the different steps involved in the design of a two-way slab restrained. I'm going to design a restrained two-way slab. Let us go to the next page here. Let us start the design. I cannot complete it in today's class, but anyway, I will just explain it. Two-way slabs, you can see restrained, unrestrained. Restrained table 26, page 91, unrestrained table 27, page number is same. Page number is same for both the, because in the same page, both the tables are there. Now let us see this problem here. Design, all of you can see this one now. You can unmute and tell me, you can see this?
Yes, sir.
Okay. So let us see this problem here. Design a two-way slab to suit the following data. Clear dimensions inside 5 meter by 4 meter. Boundary conditions. All four edges are discontinuous with corners held down. Discontinuous means there is no room other than this. Imaginary case it is actually. But many times it has come in the exam. That is, there is discontinuous means that there are no slabs are not there after this. Single isolated room it is. All four edges are discontinuous with corners held down, means restrained slab. Live load is given as 4, floor finish as 0.6, use of M20 and 415 steel. Slab is supported on 300-meter thick masonry wall. So after reading this, I have drawn this figure. So LX is always smaller dimension, that is 4 meter. LY is always bigger than this, 5 meter. Like this, you have to draw the figure. And they have given 300 mm thick masonry wall. So you show that additional thickness. So show the clear dimensions. Show the clear dimensions inside. Draw one more rectangle, one more line outside at a distance of 0.3 meter. So this is the plan of your two-way slab. Now see the steps, as whatever steps I have given in the previous slide. Check for the type of slab and determine factored load. So Ly by Lx is 5 by 4, 1.25, which is less than 2. Hence, the two-way slab is designed. Two-way slab is designed because the ratio of Ly by Lx is less than 2. Now, in the elevation, I am just showing a small d and capital D like this. This thickness of wall is 0.3 meter. Now, you have to start with a trial section. I already told you there are many formulas are there in different books to get the starting thickness, because as I told you, it is always a trial and error only. To find out D and D, assume a suitable span by depth ratio. So in case of two-way slabs, this ratio should be 25 to 35. From 25 to 35, you can assume any span by depth ratio. Somebody can say I'll use span by depth is equal to 25. Somebody says I'll use 30. There is no problem. Dimensions will be different, but the design has to be correct. Procedure has to be correct. It should not fail for a shear, deflection, and all those checks. So that is why the thing here is some range is given 25 to 35. You can choose any number between this range and decide the slab thickness. Now I have started with, let us say 28 I have taken. Randomly chosen. You can choose any number, your slab thickness will be slightly different, but it is not, there is no problem. Design is not unique. No design is unique. Solutions, you can have different, more than one solutions. Unlike analysis of indeterminate and determinate structures where solution is fixed, answer has to be same. In design subjects, it is not necessary that answer has to be same, but they should be very close values. AST should be very close. Even if the thickness, all those things, even if somebody chooses some other ratio, finally what will happen? Steel and all those things are very close to each other. So span by depth is 28. I'm going to use span by depth 28. Therefore, span is, remember always span is smaller only. All calculations are based with respect to smaller span only. It is used only for Ly by Lx. The bigger span is used only to get this ratio. Otherwise, everywhere we are going to use shorter span only. So 4000 by D is 28. D is equal to, from after assuming 28 span by depth ratio, I am substituting span here and getting D for 142.8. So after getting this number, I am rounding it off to 145. 145 and total depth is 170. Again here there can be arguments. For example, usually 15 mm is enough. I can very well go with 160 also. You can try, no problem. So 145 effective depth is 145, capital D is 170. Minimum we need 15 mm. Minimum 15 mm is enough, but I have given 25. That is why it is 170. So trial section. This is a trial section. Usually when you design beams, whether it is a cantilever span by depth ratio is different. It will not be 20 or something like that. When you are designing a cantilever beam, span by depth ratio is maybe 7 or 8 like that. That is why, see, whenever you assume these depths, trial sections, you have to be careful. Again, for one-way slab, the span by depth ratio will be different. For beams, span by depth ratio will be different. Again, for two-way slabs, span by depth is different. That is why you have to be careful about this. For every this one, you have to remember what will be the span by depth ratios, because you will get the trial section. Usually, if you follow this one, the trial section will be almost workable. Means it will not fail usually if you use these thumb rules. So let us go to the next page. This one you can see here. This one is load calculation. Still step number 1 is not over. So dead load. See, 1 meter by 1 meter is taken in design of slabs for calculation of loads. See this load calculation 0.17, which is 170 mm overall thickness into 1 meter 1, this volume of concrete into density. Volume is in plan 1 meter by 1 meter, thickness is 0.17, 25 is the density. So you'll get 4.25 kN. Imposed load, that is live load, 4. It is given in the problem. Floor finish is given 0.6. Usually it is 1 they are giving. Usually floor finish is taken as 1 if it is not given. Otherwise, whatever is given, you have to use that value. Total is 8.85. Add this 8.85. Finally, we have arrived at factored load of 1.5 times this, 13.3. Usually a practical man, what he will do, he will go with 15 here. He will say, I will use 15 and he will solve it. because nothing will happen. But in the examination, you stick to this number only. Now, step 2, effective span factored BM and MU limit. This is also quite simple here. Effective span is smaller of center to center of bearings or clear span plus effective depth. Now, since this thickness is 0.23, I think it is 300, no? Okay. So, that is why center to center has become 4.3. Here 0.3 3 by 2, here 0.3 by 2. Okay. Otherwise, I need to change it. If it is 0.3, s 0.3 only is given. So it is 4.3 it is. One calculation is clear span plus bearings, or second is clear span plus effective depth, which is 0.175. So 4 plus 0.175 is 4.175 it is. I mean small d it is 145, that is 4.145. So out of these two, the smaller is 4.145. See this. So effective span along the direction x is 4.145. Along the direction y is 5.145 because the other dimension is 5 meters. So 5 plus 0.145, that is along y direction effective span is 5.145, even though it is not used anywhere. So along x direction 4.145. How to find out the bending moment? You cannot use WL square by 8 and all here for two-way slabs. Separate procedure is there. Carefully observe this one. Factored bending moment along short span I have to calculate. Factored bending moment along long span I have to calculate. So this is what we call it as IS core method. Okay. Now observe here. First I'll calculate alpha ux. I mean MUX. If I want to find out factored bending moment along short direction, you can see this one. I'll be using this formula. So WL square by 8 and all is not there here. Alpha x into W into LEX square. Now before what is alpha x, you already know WU and LEX. These two terms already you know it, where they are, that is LEX is 4.145. So LEX is effective span along x direction, it is 4.145. WU is 13.3. WU is 13.3. It means you know already two values in the RHS of MUX formula. How to find alpha x? Alpha x depends on whether the corners are held down, whether it is restrained or what. Okay. So let us see this one, how to find alpha x. Let us not worry about MUY presently. Let us look at alpha x. Already WU and LEX, you know it. You have to see the table actually. Observe this. As the corners are held down, table 26, page 91 will be referred to calculate alpha x and alpha y values from the boundary conditions given. So this is alpha x is Ly by Lx is equal to 5.4, 1.25, case 9 of table 26. I'll take you to that page here. I'll show you how to calculate alpha x, which is very important. Let us see how it can be done. It is on page number 19 of this particular presentation. It's 19. Carefully observe this. This page number is, see, page number is 91. This page is enough. This page is enough here for calculations. Now let us see what it is. So bending moment coefficients, that is alpha x values and alpha y values also. For rectangular panel supported on four sides with provision for torsion at the corners. Restrained slabs. Restrained two-way slabs. Table 26. Page number 91. Now what I should do here is, okay, just observe how to use this table first. How to use this table. Now you look at this line. Along this line you go here. You go along this line like this. 1 is there, 1.1 is there, 1.2 is there, 1.3 is there, 1.4 is there, like that. This is nothing but Ly by Lx ratio. If it was 4 meter by 4 meter, alpha x is 1. Okay, like that. See, like that it is, as the ratio is depending upon the ratio it is. Ratio is Ly by Lx. Now in our case, this is one thing. Second is short span coefficient alpha x, long span coefficient alpha y. So I'm going to get alpha y here in the last column. Alpha x, it can be anywhere here. Your alpha x value is anywhere in this area now, depending upon how you are going to understand this. Now observe, the boundary conditions are given. Type of panel and moments considered. It means column 2 is boundary conditions. Now I'll show you where I should go here. I'll go to the table, ninth boundary condition, last one. All 4 edges are discontinuous. There are no rooms, only isolated room is there. All are discontinuous. Slab is not going beyond the support because only one room is there. So all 4 edges are discontinuous. They are not continuous. So discontinuous. So positive moment at the mid span. It means I should look at this boundary condition. Mainly they are giving 2 conditions. One is 8th or 9th. For any condition you can calculate, there is no problem. Out of 9 boundary conditions, any one condition will be given in the problem. Okay. So in this case, after reading the problem, I am able to understand that I should go corresponding to 9th case. 9th case is all 4 edges are discontinuous. Now how to calculate alpha x? So this is table 26. Now I'll go to that page again. You can see this alpha x calculation. So table 26 I have shown you on page number this one. Now alpha x depends upon the ratio Ly by Lx and boundary condition. Case 9 is matching. Whatever boundary conditions are given in this problem, case 9 is matching because all 4 edges are discontinuous. Ly by Lx is equal to 1.25. There is no 1.25 there, I think. See this, you have to interpolate now. Again you can see here, Ly by Lx, 1 is there, 1.1 is there, 1.2 is there. So ours is 1.25. The problem alpha, that is Ly by Lx is 1.25, which is in between these two. You have to interpolate it now. So I should go to this one here, 1.2, 1.3 is here. I'll go down because I have to see that the boundary condition. So you can see this here, 1.2, 1.3. So I should look at these two numbers. I should look at these two numbers. 1.1 and 1. Say, I'll just zoom out here. I have taken two values corresponding to 1.2 and 1.3. So corresponding to 1.2, it is 0.072. Corresponding to 1.3, Ly by Lx, it is 0.079. I need to interpolate what will be the value of alpha x if Ly by Lx is 1.25. I think you know this how to interpolate now, because corresponding to 1.25 alpha x, the value will be in between these two numbers, 0.072 and 0.079. This is what you have to do in case of table 26. Look at the boundary conditions given, look at the alpha, that is Ly by Lx ratio, then try to find out alpha x by interpolation. it means you should understand in this way. First, see the Ly by Lx ratios. If it is already there, no need to interpolate. If it is in between these two numbers, then you extract these two values and find from these two numbers, find out the alpha x corresponding to Ly by Lx of 1.25. You have to interpolate it now. So let us see how it is done. Interpolation and all. Already, I will not waste much time on that actually. See this. I have written like this here. From the boundary conditions given in the problem, case 9 is applicable. So alpha x 5 by 4 is 1.25, case 9, page 91. Now how I have done this one, table 26, case 19, 9, alpha x is having for 1.2, 0.072, for 1.3, 0.079. What is the value of alpha x for 1.25 Ly by Lx ratio? By interpolation, I have done it 0.076. You have to do it actually. Actually, you should do it. You have to interpolate it. This is interpolation. Now look at this number. It is in between these two. It should be in between these two numbers. So 0.076. Once you understand this one, you can easily find MUX, factored moment along shorter span along x-axis. What I have done here, alpha x w into L square. So 0.076, this value is taken here. W is 13.3, LEX square, effective span along x direction. I am getting a value 17.33 into 10 raised to 6 Newton mm. Usually it is written in terms of 10 raised to 6 because I can simply write 17.33 kilonewton meter. Simply I can write kilonewton meter also, but usually we need in Newton mm only for calculations. Now, how do you find alpha y? Now you can look at this particular number here. See this one. What is this? It is alpha y. Alpha, see, MUY means bending moment in the y direction. So how to understand this one is, let us say this is your how to understand these things, observe this here. So this is the strip here. Imagine like that. This is one more strip here. See, because of the two-way slab action, both the strips are bending. This strip bends like this. This green color strip, okay, it bends like this. And this strip, because the bending takes place in both the directions, so this strip bends like this. Here also supports are there. Because here also supports are there. Here supports are there. Here supports are there. That is why the strip, which is in this color, it bends like this. Green strip bends like this. That is why bending moment is taking place in both the directions. So I have to find out MUX. Green strip is MUX. This one is MUY. Okay. Now how I got 0.056? It is very simple in this case. In this case, it is quite simple. I'll go back to the table. Alpha Y, how I got it? Just see. Alpha Y is just simply it is this 0.056. No need to calculate it, because it does not depend upon any interpolation and all. Because see this long span coefficients for all values of Ly by Lx. It means Ly by Lx can be anything for calculating alpha y. When you calculate alpha y, directly go to the last column. For last column of case 9, it is 0.056. I think you can follow this one now. Calculation of alpha y is very simple. Alpha x requires interpolation. So here what I have done is, see this one. Now I have calculated MUY alpha y WULEX square. Very important observation is this. Very important observation is, in both the cases LEX has come. Nowhere LEY will come, even though the constants are calculated like that only. You cannot use LEY square here because it is bending moment in this direction along the y direction. So bending moment along y direction also has the same span. Along x direction is also same span. In that way only these constants are adjusted. So that you can use in both the cases short span only. So this will give your MUY as 12.8 into 10 raised to 6 Newton mm. Okay. So now you have to, after getting these two, find out MU limit 0.138 FCK BD square. As you know, in case of slabs, B is always 1000. D is whatever is we are having it 145. FCK is there. You are going to end up with MU limit as 58.03. You can see this into 10 raised to 6, which is more than these two values. It has to be more. 17.33, 12.8 is 58.03. It may be uneconomical also because the depth is more. So usually it is an, as you know, it is an iterative procedure. Design is always trial and error. If I want, I can go back, I can reduce the thickness, and once again I try to see that these two are very close. But in the examination, all those possibilities are not there. You have to just proceed with the next as long as it is safe. As long as MU limit is more than factored bending moments in both the directions, it is safe and under reinforced. So MU limit is more than MUX, more than MUX as well as MUY. So depth assumed is adequate and section is under reinforced. So when I say MU limit is more than MUX, MUX why I have written? Because higher value I have chosen here, higher of the two. Anyway, it has to be more than these two. So higher is MUX, that is why MUX is written here. So MU limit is more than MUX. There will be two conclusions. Conclusions are depth is adequate, section is under reinforced. Two conclusions can be drawn once this condition is satisfied. Now here what we can do, AST, use this formula, find out steel 349.4, or the best is use SP60. You will get a number which is very close to this. Already I have explained it once. Find out MU by BD square, go to table number 2. I don't know whether the table is there in this, for the second, whether it was loaded or not. I think it is here. Once again, I'll repeat it, observe this. Table 1, it is. Table 1 I cannot use. It is, there is a problem with this this page. It is 1.5 actually. In the book only it has given. There is a misprint is there. So this is actually, this is not 2. This is 1. Table 1 is, in the book only that is misprint is there. It is 1.5. FCK is 1.5. Table 2 is FCK 20. Table 1 is FCK 15. Normally nobody is using. Table 1 is not used anywhere in the design of RCC structures because M15 is no longer permitted. So no question of using table 1 anywhere in RCC subject. Only you can use table 2, which is here. Why table 2? Because FCK is 20. So like this, you have to find out MU by BD square. Then under FY, that is 415, you check wherever that, find out the value of PT. Again, this is equated to AST by 100 into AST by BD into 100, where B is, remember, 1000. So that procedure is better actually, but I have not done it in this case. To try that one. Now where we are, actually we are at this stage now. Reinforcement I am calculating. I have calculated MUX and MUY. Along MUX, I have to use that bending moment. What it means here is, if I want to know what is the reinforcement in the shorter span, I have to substitute MUX here. See this. MUX is substituted, then AST is calculated. That is what is AST in the X direction. So what it means here is, what it means in this case is, you can see this. What I'm trying to do here is, I'm trying to find out steel in one direction, this direction. If I want steel in this direction, in this formula, MUX has to be used. Rest all will be same. Depth may change. Depth will change slightly. I'll tell you why it is. So I end up with 349.4. I'm telling you again and again, instead of this, go with table 2. Okay. Next, ASTY. Again, ASTY is, you can see here, again use the same formula. You can use the table 2 once again here. Only thing is that MUY value should be used. Everything is same. Now the depth reduces here. Depth reduces because it will not be 145 because 145 minus again half of the diameter. Because you see this reinforcement how it is placed. Shorter span steel is below. Above that, longer span steel will come. When you place two bars like this is the shorter span steel rod it is. Then you are going to place longer span steel like this. Okay. What will happen to the depth here? Depth becomes less now. Depth up to the center of long span steel. This is the depth. Whereas center of this short span steel is which is 145. So this is 145. When you calculate ASTY, depth has to be revised because it is how much it is now. Up to this it is 145 minus the diameter. I'll show you accurately here. See this. See this is 145. In 145 you subtract this much. Half of diameter this side, half this side. Totally 8 mm because 8 mm bars are used. So 145 minus 8. Total is 145 minus 8. It is 137. So like this, you should use a revised depth. Depth has to be less for ASTY. So when you calculate using table 2, same procedure is MUX by BD square. So B is 1000, D will be 137 M. Is it okay? I'll just stop it. After this, I'll stop it now. ASTY is 264. One more thing is you have to check before you finalize the bars. AST minimum should be checked. So AST minimum is 204. AST minimum is 204. Now again cross check whether this value is more than ASTX and ASTY or what. If this is more, you have to use this one only. In this problem, both ASTX and ASTY are more than minimum that has to be provided in any case. In any case, it has to be. But what has happened here? Anyway, this is less only. So we are not going to bother. Whichever is more here along AST, along Y direction, 264 is the steel required. Along X, that value 334, something like that. 349 along X direction. Like this, you have to calculate the reinforcement, and already I have chosen the diameter as 8 mm. That is why I am able to calculate the depth in both the directions. So finally, spacing and all, I'll discuss it in the next class only. Next 5 minutes, I'll take the attendance. You go. I'll just share these notes. Complete design of one-way slab, complete design of two-way slab. Both the notes I'll be giving. Just go through that one. Then you have to refer the question paper problems. That also I'll give you. Textbook notes if you want. I'll just that also I will scan and send it. Additional problems are there. Those also I'll send it. Just solve one or two problems first. Then